Good afternoon, everybody. Myself Akshay Jilova, I am from GPCG Jalandhar, and I am here to discuss the subject microwave and radar engineering. In this today we will be discussing the topic MTI radar and display. So, before I move on to MTI radar directly, I would like to give some introduction to radar engineering, what the radars all about are. The radar is the acronym radio detection and ranging. Principle of operation of radar is theory of reflection. Here the signals are transmitted, they got reflected from the object and then they are received by the receiver antenna, and the total time difference is used as the measure of distance, or if some other quantity means direction, velocity or some other parameter is to be measured. For that, the reflection is the basic principle. So, basic principle of radar is theory of reflection. Next is location parameters. In radars we find out the ranges, the height, the direction of motion, relative velocity. So, these are some of the areas of application of radar. We can find out the range of any object which is at a far off distance from the radar, then height, direction of motion, relative velocity. And requirement: high transmitter power. Suitable oscillator for this is magnetron. This is one of the oscillator which is used for generating microwaves. Applications. Now, we will discuss the applications of radar. Navigational aid on ground and sea. Radar altimeters, this is used for height measurement. Radar blind lander, it is used in aircraft landing during the poor visibility. When visibility is not there, the pilots use this system to aid the landing of the aeroplanes. Then airborne radar for satellite surveillance. There are different types of radar, some are airborne radar, these radars are used for surveillance of satellites. Then space applications like planetary observations. Other applications are police radars, these are used for law enforcement and highway safety. Normally, you would have seen those radars or the banners put on the roads that you are under radar surveillance. So, these are the radars which are used by the police personnel for law enforcement and also for control of speed of vehicle on the road. Then radar for determining the speed of moving targets can also be detected as far as their speed is concerned by using radars. Then remote sensing, weather monitoring, we can use radar for the calculation and determination of weather also. Then air traffic control and aircraft safety, this is very important application of radar. In air traffic control, we use the radar system, as well as for aircraft safety we use radar system for controlling the traffic of aeroplanes on the in the air as well as on the ground, we use radar system. Then next is ship safety. Ships are also navigated by using the radar system. Next is non-contact method of speed and distance in industry. So, this is a very important application of radar, non-contact method of speed and distance in industry. In the industries, there are some areas where human beings are not allowed to go, or where it is not safe for a normal human being to go, but the parameters of that area are to be known, and that is done with the help of radar, whether it is speed or distance in the industries. Next important application of radar is in military or defense we call it. These are number 1, detection and ranging of enemy target even at the night. So, during the night when visibility is not there, we can use radar system for detection of ranging of the enemy targets. Next is aiming guns at aircrafts and ships. Aircrafts and ships of the enemy can be targeted by using radar. First they are to be detected, and when you know the exact distance and location of the target, it can be targeted by using radars. Next is bombing ships, aircrafts or cities even during nights. You might have heard of the Air Force. So, Air Force personnel normally use radars for the bombing operation or combat operation during the battle. So, even during the night, it is not difficult for army persons to locate the various cities or ships or aircrafts of the enemy for bombing. Next is early warning regarding approaching aircraft or ships. As radar can be used for detecting targets for bombing or for combat operations, similarly the radar can also be used for defense also. So, if some missile or some aircraft is approaching a particular target or a particular location, that can also be detected by radar, and the necessary safety measure can be taken. Next is directing guided missiles. Nowadays guided missiles are used, these are the long distance missiles, and they can detect and target a particular location at a far off distance from the location from where the missile is being fired. So, that is done with the help of radars, and throughout its motion from the area from where it has been fired to the target or the location where it is supposed to be targeted, it is guided by the ground station, and these guided missiles are used by, and for this we use radar. Next is searching for submarines, land masses and buoys. Submarines, land masses and buoys in the sea operation can also be searched by using the radar system. So, these were some of the applications. Now, we will discuss the basic radar, what the radar is. This figure shows the basic radar. Here we have a transmitter, a receiver and a duplexer. This is very basic structure of the radar. The duplexer is connected with the antenna, and here this circle is nothing but it is the target. So, how the radar operates in its simplest form, what we do, the signal is transmitted from the transmitter via duplexer. So, what the duplexer is? Duplexer is a device which works in two modes, TR and ATR, and duplexer connects either transmitter or receiver one at a time with the antenna. So, here you can see there is one antenna, and the same antenna is being used for transmission and same is being used for reception also. So, what duplexer does, for one instant it connects transmitter with the antenna, this connection is activated. So, signal is transmitted through duplexer, it goes to antenna, and from the antenna it is transmitted. These arrowheads which move from antenna to the object, they show that signal is being transmitted. After the transmission of signal for once, means one pulse or one signal when it is transmitted, after that what happens, this duplexer disconnects the transmitter section and now it connects the antenna with the receiver. So, what happens, when signal strikes with the object, it gets reflected from the object, and after getting reflected from the object, signal travels back to the antenna, and now the antenna is connected to the receiver section. So, now when signal comes back, it is connected to the receiver section. So, it goes to the receiver from where it is detected and then it is fed to the indicator. Now, indicator is nothing but it is the display device which displays the actual range of the target. So, when signal is transmitted by the transmitter, then you can see from here a contact is given to the indicator also. So, at the same time when the signal is transmitted from the transmitter, at the same time the reference signal is sent to the indicator, which marks the beginning of the time location, the time. So, this time clock is triggered on when signal is transmitted, and time clock is triggered off when signal is received through the receiver. So, total time difference between the signal transmitted and the signal received is calculated, and that time gap shows that this is the time taken by the signal to travel from antenna to the object and then from object to the antenna. So, this is twice the journey. The distance from the antenna to the object is travelled twice. So, actual time taken by the signal to travel from antenna to the object is half of the total time. So, that time is divided by 2, and then we calculate by knowing the velocity of the signal, as these are EM waves, we can find out the distance of the object, because time is known, speed is known. So, we can find out the distance of the object. So, that distance is nothing but it is range of the object. This has been explained here. The distance of target can be calculated from the total time t taken by the pulse to travel to the target and return to its original initial point. Assuming c to be the velocity of light in free space, the distance travelled by the pulse is ct meters. Now, this is 2 times the target distance, hence the distance to the target r is ct by 2 meters. So, this is clear from here, because c is nothing but this is velocity of light, and electromagnetic waves travel with the velocity of light. So, we know the velocity, we know the time, we can calculate the distance, which is called range also. We divide the total time by 2, it is t by 2, multiply it with the velocity, because velocity is distance upon time. So, distance is velocity into time, time is t by 2, c is the velocity. So, range can be calculated. Requirements of a radar system: automatically operating duplexer, transmitter should remain silent during the echo period. So, this is what I have explained earlier. Automatically operating duplexer means duplexer connect once the transmitter with the antenna, and then, as the second point makes it clear, transmitter should remain silent during the echo period. This means the duplexer is automatic. Once the signal is transmitted, transmitter goes silent, because now the duplexer connects the antenna to the receiver section. Transmitter pulse should be very powerful. This is one of the prerequisites. It should be powerful enough, it should have strength enough, so that it can travel from the target to the antenna and antenna to the target. So, it should be a strong signal. Receiver should be highly sensitive to echo signals and should be highly immune to the noise. Receiver should be highly sensitive to the echo signal. There will be echo signal which is very weak, because when signal travels from the antenna to the target, it is scattered throughout, and when it is reflected back from the object, it comes back to the antenna. So, a lot of power is lost during its journey from the antenna to the target and target to the antenna. So, the receiver should be very sensitive, highly sensitive, because the echo signal normally is very weak. So, it should be sensitive enough to detect that signal, and it should be highly immune to the noise also. The receiver should be such that it should not respond to the noise, it should be able to differentiate between the noise and the actual signal. Next is antenna should be highly directive with large gain. So, this is also one of the prerequisites, very important requirement of the system, that antenna should be highly directive with the large gain. Gain means the directivity of antenna should be more and it should be highly directive, means when signal is being transmitted, it should be transmitted in the direction of target only. The maximum effort should be there, that it should be directed towards the target and it does not get reflected otherwise. Next is pulse repetition frequency should be high compared to the scanning period. Now, what pulse repetition frequency is? This is the duty cycle per pulse width. This is called PRF also. It should be high compared to the scanning period, means there should be much time, much available time, so that the signal can be transmitted and it should be there should be time enough, so that it can be received at the receiving end. Now, these are some of the frequency band designations. This table shows band designation and nominal frequency range. HF 3 to 30 megahertz, VHF 30 to 3300, UHF 300 to 1000 megahertz, L 1 to 2, S 2 to 4, C 4 to 8, X 8 to 12, KU 12 to 18, K 18 to 27 and Ka 27 to 40 gigahertz. These are the frequency ranges for the radar system. So, if a particular radar is being operated at a particular band, so we should know that which band the radar is being operated on. Next is classification. Continuous wave radar or Doppler radar, this is another form of radar. Continuous wave radar utilize continuous waveforms which may be considered to be a pure sine wave of the form of cos 2 pi f naught t. Spectra of radar echo from stationary targets and clutter will be concentrated at center frequency f naught, for the echoes from moving targets will be shifted by the Doppler frequency. Thus, by measuring this frequency, difference CW radars can very accurately extract target relative velocity. Because of continuous nature of CW emission, range measurement is not possible without some modification to the radar operations and waveforms. So, CW radar is continuous wave radar. This is another form of radar, as we just have discussed the pulse radar. In CW radar, continuous waves are transmitted, and here we have two different antennas, transmitting antenna and receiving antenna. As we saw in the case of pulse radar, it was only one antenna which was being used for transmission as well as reception by using a duplexer there. But here in CW radar, this is not possible, because signal is being transmitted continuously, and when it is transmitted like that, when it has to be received, it has to be received somewhere else, and it is received at the receiving antenna. And at the receiving antenna, what do we have? We have the Doppler frequency shift. Doppler frequency shift is what? It is nothing but it is the concept is that when there is a relative velocity between the target and the object, target and the transmitter, then there will be a Doppler frequency shift. And what that Doppler frequency shift? It is directly proportional to the relative velocity. Relative velocity is what? At the velocity at which the target is moving and the velocity at which the transmitter is moving. So, difference between these two velocities is relative velocity, and depending upon that difference, there is a shift in the frequency, whether either that frequency will be somewhat higher than the transmitted frequency, or that will be somewhat lesser than the transmitted frequency, depending upon the direction of motion. So, if the target is approaching towards the transmitter, then it will be the plus sign, Doppler frequency shift will be some added frequency to the transmitted frequency, and if it is receding or moving away from the antenna, then that will be bearing a negative sign, and the received frequency will be somewhat less than the transmitted frequency. Pulse radar we already have discussed. This figure shows how the pulses are generated. More useful than CW radar, here the transmitter transmits a train of narrow rectangular shaped pulses modulating a sine wave carrier. The range of target is determined by measuring the time taken by the pulse to travel to the target and return to the radar station. This is the pulse, this is reset time, again pulse, again reset time, again pulse. So, this is called radar carrier frequency, and this duration is pulse repetition time PRT, or this also determines the pulse repetition frequency also. 1 by T is pulse repetition frequency. Now, we will discuss something about radar range equation. Radar range equation relates the range of the radar to the characteristics of the transmitter, receiver antenna, target and environment. It is used for radar system design. Whenever we have to use radar, we should know what the radar range equation is, because whenever we have to calculate the range, it is calculated with the help of this equation. How the equation is derived? This is these two figures, first and second, they show there is a radar and this is isotropic radiation pattern. Signal is transmitted, this is the range. How the range can be calculated? When we transmit a signal, means if the antenna is not very directional, then what will happen? The signal will be scattered all over the radar. When we transmit an antenna, a signal from an antenna, what happens? It scatters all around the transmitter, and at a particular distance, say r, which is called range of the radar, if we have some object, what will be the signal strength which will be reaching there? It will be total signal divided by 4 pi r square, because if this r is taken as radius of a sphere, it scatters all over the sphere. So, this is P t over 4 pi r square watts per meter square. Here, if we use a radar which is directional, now you see the difference between these two figures. This is isotropic radiation pattern, means an omnidirectional antenna or an omnidirectional radar, and the next is this is directional radiation pattern. Here the radar has got some directivity. As I said earlier, one of the prerequisites of radar is that it should be highly directional, or directivity of the radar should be high. So, here we have used an antenna, and this has made, what the difference has been made is that the signal which was scattered here all around the antenna, now in this figure you can see that signal has been zeroed in a particular direction, that is concentrated or focused in a particular direction, and it travels, maximum strength of signal travels in this direction. So, if antenna used here has some gain which is G is the gain of the antenna, then what will happen? By using such an antenna, what will be the signal strength which will be reaching here at a point which is at a distance r from the transmitter, will be P t over 4 pi r square G, where G is the gain of the antenna. So, this is the factor by which the strength of signal has been increased in a particular direction, or the strength of signal which is reaching at a particular location is higher by this factor G. Higher the G, more will be the signal strength which will be reaching at the object. This is an equation which shows the maximum range of radar. This is called R max. R max means maximum range of radar. By using a specific radar, what is the maximum range which can be calculated by using that radar is given by this equation R maximum. Suppose you have some radar, what will be the maximum range over which that radar can be used practically? you can calculate that by using this equation. It is the distance beyond which the target cannot be detected. When I said maximum range, it means that is the maximum range. If target is further away from that point, then it will not be able to detect that point by using that radar. So, for that we will have to use some other radar. This happens when when P r is equal to S minimum, which is minimum detectable signal. P r means received signal, as P t was transmitted signal, P r is received signal. So, that received signal should be equal to S minimum. Now, what that S minimum is? Minimum detectable signal. So, as radar is made up of some electronic material, or there are some devices which are being used for radar. So, the circuit by using which you are you have made some radar, that will be having its higher and lower limitations. So, what is the minimum signal which can be detected by using a particular radar or a particular circuit, that is predefined. So, if the signal strength is lesser than that, or if the signal is weaker than that, then that signal will not be determined by that radar. How and why? Because that signal strength is not enough to trigger the receiver circuit on, and when the receiver circuit is not triggered on, we cannot have a received pulse, or we cannot we do not know, we can't know that whether the signal has been received or not. So, if we do not know whether the signal is received or not, we cannot calculate the range. So, minimum signal which can trigger the receiver circuit on is called S minimum, and this is the signal which is which gives you the maximum range. Lesser the S minimum, more will be the range, as it is clear from here that it is inversely proportional to R maximum, means lesser when the signal will be lesser if the target is further far away. So, this is the maximum range of the radar for which signal is minimum. Maximum range, the factors on which the R max depends is P t, G, A e and sigma. This is called radar range equation. Factors affecting the range of radar: transmitted power, the frequency, as lambda was there, it is a measure of frequency, radar cross section of the target, minimum received signal power, means S minimum. So, these are some of the factors which affect the range of the radar. Next point is maximum unambiguous range. Once the radar transmitter transmits a pulse, sufficient time should be allotted, so that the echo signal due to this pulse may be received and detected before the next pulse is transmitted. If PRF is too high, echoes may arrive after the transmission of next pulse. Such echoes are called R unambiguous, and this is whichever the time after that echo comes is called that time around echo. Means, suppose you have some signal here, this is these are some of the pulses, train 1, train 2, train 3, means if a signal is transmitted and as per PRF, next signal or next pulse is also to be transmitted. So, it is clear from this picture. Suppose one pulse is transmitted and we are waiting for received signal, but no echo is received. During you can see from here, there is no echo signal which is received, and the time has come for transmission of next pulse. So, what the duplexer will do, it after this much time, it will connect the antenna to the transmitter section, and again the pulse will be transmitted. So, when this pulse is transmitted, after some time, here E 1 is the first echo signal, you receive one echo signal. Now, here the problem or the confusion is that this signal is transmitted and we are waiting for the echo signal to come. Again a signal is transmitted and we are waiting for the signal, and here the signal comes. Now, this received signal has come, but we are not sure from where this signal has come, whether this is the reflection of T 1 or it is reflection of T 2, it is not known. So, this gives a confusion, or which is also called ambiguity